Okay, good afternoon. So we continue the lesson of differentiation rules. It is actually exactly the knowledge that you need from Math 3C. So let me just try to finalize this lesson today. So this is the table we actually developed last time, if you remember. So we have these formulas for different functions. And then we have some generic rules. There are three more rules that I will add here, and some more rules that we will add here when we are progressing in this course. But for the time being, that is enough to be able to solve these problems. So the point is we want to differentiate the following functions. So differentiate means find the derivative function. Okay, so you need to, because you see that this is a diversity of problems, even though the table seems a little bit dull, they are not that diverse, but you see that using those formulas and the formulas on the left, you can combine and make new functions out of it. Okay, let us practice a little bit because that's extremely important to be able good in differentiation. Okay, so if you want to do this, let us just do it one by one. So if I want to do this one, this is a function which is not directly in that table. So I have to change the form of the function in a way that I can use the formulas there. I don't think that's a hard problem. So you start number one here. You expand, yes? So before differentiation, you have to put this in the correct form. Okay, so this becomes 4. So you know that here it is important to know, if you want, I can also add these formulas here, but they are not differentiation rules. So let me write them with a different color. So these formulas that are also good to know. Square root of a can be written as a over 1 over 2, a to power 1 over 2. The nth root of a can also be written as 1 over n. And then the nth root of a to the mth is a to the power of m over n. These are not the differentiation rules, but it's important to know about them as well. Okay, so here I use that formula here, so this becomes the third root of x can be written as x to power 1/3. And then, of course, you understand that I have to expand that. Of course, later we will also learn about what is called the chain rule and the product rule. If you like, you can use those rules without expanding them. But still, even though I know those rules, might be in this case, it is easier to expand. Okay, so that is something that you don't need to forget, even if you learn the chain rule, even if you learn the product rules. Okay? But sometimes it is not possible. For example, let me just make a very simple example right away. If I multiply x by e to power x and ask you to differentiate that, you cannot do it under any circumstances. Then you have to know the product rule, because there is no way. Of course, if I ask you, do you know the derivative of x? It is extremely simple. Yes, it is 1. The derivative of e to power x is e to power x. But there is no way that you can find the derivative of this very simple looking function if you don't know the product rule. Okay? So sometimes you really have to know the product rule. So for this simple function, you have to wait a little bit to see what the product rule is. But even though this function looks more complicated than that function, but still you can solve it without the product rule, because I can expand. Expand this one. The first one to power 2 is x to the power of 4. 2 times the first one times the second one is minus 2x squared, and the second one to power 2 is just 1. Okay, let us just do some part of it in our head, yes, because now easy. So I multiply this in, these bases are the same, so I add the powers, so I know how to do that in my head. So this becomes x, 4 plus 1/3 is 13 over 3, yes? And then I multiply that here, so this becomes minus 8, x to the power 2 plus 1/3 is 7 over 3. And then I will have 4 x to the power of 1/3. Now everything is ready, so I can differentiate it. My function is a composition of 3 functions, and I have multiplicative constants, So all these three rules on the left side is needed. But let us just do the calculations as simple as that, as simple as possible. So I just take the derivative of this one, 13 over 3 goes down. It will be multiplied by 4, so this becomes 52 over 3, x to the power 1 unit less. 13 over 3 minus 1 is 10 over 3. These simple calculations, I go a little bit faster this time, but if you don't understand, stop. Okay, then this will go down, so 7 times this is 56 over 3, x to the power of 1 unit less, it is 4 over 3, and then this one goes down, so 4 over 3, x to the power 1 unit less becomes negative 2 over 3. So that is the derivative of my function. Mainly my concern will be differentiation. Of course, if you want, you can write it different forms, going back to the third sign and things like that. But let us stop here, okay? So this is the answer to the first part of this question. Okay, so now we go number 2. So number 2 is this function. Again, the same story. This function is not exactly in my table, so I have to change its form. So I expand it again. So g of x becomes equal to the first one squared, which becomes e to power 4x, 2 times the first one times the second one. Let me just momentarily write it. And the second one to power 2, so which is e to power minus 4x. But then e to power 2x times e to power minus 2x is what? E to power 0, which is 1. Yes? So then it becomes just 2. So g of x is equal to e to power 4x. Let me write e to power minus 4x next to it. And e to power 2x times e to power minus 2x is e to power, when you add them, it becomes 0. E to power 0 is 1 times 2 is just 2. And now everything is ready to differentiate. And it is clear that you need to use this formula that you had it in Math 3C, yes? Both here and there. So if I take the derivative of this one, 4 goes down, e to power 4x. Here, minus 4 goes down, e to power minus 4x. The derivative of 2 is 0. So that is the derivative of this function. Yes, that is also good to know these formulas here. These are special cases. So if I choose C to be 1, then this is interesting to know that if I choose C to be 1, then this becomes function e to the power of x. If I want to take its derivative, C is 1. So that is interesting. This is a function whose derivative is exactly equal to itself. And if I ask you what is the derivative of e to power minus x, then you choose C to be minus 1. If you choose C to be minus 1, then it becomes minus 1 times e to power minus 1 times x, which becomes this. Of course, these extra formulas are not in the formula sheet. The ones in blue you will get in the formula sheet. But these are special cases. For these cases, I really recommend you to remember them. Of course, everyone hopefully knows the derivative of x is 1, but that is also very important to know. Okay, so let us go back here now. So number 3. So number 3, we want to differentiate it. So that's also very simple, yes? So number 3, h of x. You know that we have to expand. So this is power 2, so I have to keep it for the time being. So this becomes e to power 2x. I expand the other one, which becomes the first one squared, which becomes e to power 6x. 2 times the first one times the second one, which gives me 4 e to power 3x. And the second one squared, which is 4. But it's still in a product form, and we don't have the product rule yet, so I just continue. I multiply this in, what will be the answer? This becomes e to power 2x times e to power 6x, which becomes what? 8x. Because the exponents are the same, I add these two exponents. The bases are the same, I add the exponents, so this becomes 8x. The same story, I multiply these two, so it becomes 4e to power 5x, and then finally 4e to power 2x. Now everything is ready, so I differentiate it. And I am using, for all of them, I use the same formula here. So this becomes 8 e to power 8x. 5 goes down, there is a 4 here, so this becomes 20 e to power 5x, and then 2 goes down, it becomes 8 e to power 2x. So that is the derivative of the next one. Okay, so let us talk a little bit about here. This one is a quotient, and we haven't studied the quotient rule yet. But this is one of those cases, like this one, that we didn't know about the product rule, but still we were able to solve it. This is also one of those cases that we can solve it even though we don't know the quotient rule yet. And even if you know the quotient rule, I will never use the quotient rule to solve this, because I prefer the method that I present here. Quotient rule is a little bit complicated. Even if you know about it, whenever you can avoid it, I recommend you to avoid it. For example, this is one of those cases that you can avoid. How? We had this in math 3C. I discussed about these things. Does anyone remember how to solve that? Yes?
We could just separate it.
Separate, yes. So you say this one divided by that plus this one divided by that minus this one divided by that. So that's the idea. So this is the idea. If you have a fraction a plus or minus b plus or minus c plus or minus etc. divided by d, if you want, you can do them separately. You can write a over d, b over d, c over d, and if it is plus, you put plus, minus, or minus. Yes? So this is the idea. Okay, so number 4, we use this idea. So k of x is equal to, so I take the first one divided by the whole denominator. So this becomes, let me be patient and write everything in detail now. And then the next one is plus 6x divided again by the denominator, but the third one is negative. So it becomes negative 1 over 4x squared. This is the first step. So if you don't if you don't remember this trick, might be this become hard for you. So remember this, I put a star here because usually people forget about it. Okay, then what we do, we simplify. Still, differentiation cannot start yet. X squared and x squared are simplified, so I get 5 over 4. And this 4 and 6 also can be simplified, 3 over 2. X's can also be simplified, but because I have this in my memory, I told you this 1 over x, I have it in my memory. I want to use it. For this reason, I just put 1 over x here. Yes, so 6 over 4 is 3 over 2. 1x and 1x are cancelled. So 1 over x is left. In principle, if you don't have this formula in your memory, I told you that the green ones are not in the formula sheet. So you have to bring everything up so that you can use that formula. But here, I do not have this anymore in my memory, so I would write it minus 1 over 4. Then x to the power of 2, I bring it up, becomes x to the power of minus 2. And sometimes I realize people still have difficulty with this. Let me just try to explain it here. So 1 over 4x squared is another name for 1 over 4 multiplied by 1 over x squared. I hope that you understand this point. Okay, then what I did, I kept 1 over 4 as it is, and then I bring this up, it becomes x to power minus 2. So this is why I really prefer you to be able to write this quickly. Okay? Okay, now everything is ready, and if you don't mind, let me put a dot here to make it clear that that's product. So I take the derivative now. This is just a constant. The first row tells me the derivative of a constant is 0. But here I need two rules, yes? One of these rules here, a constant multiplied by a function, its derivative is the constant multiplied by the derivative. So here, I don't care about the constant, I just copy and paste it here and multiply it by the derivative of 1 over x. Because I have it in my memory, I use it. So it becomes minus 1 over x squared. But this one, minus 1 over 4 again, I use this rule to separate the constant factor. And then I use this rule, the second row, to answer this question. So this comes minus 2 down, x to the power of minus 2 minus 1, which is minus 3. And of course, I prefer to simplify this a little bit here. So minus times that, it becomes minus 3, 2 times x squared. And then minus 2 times minus of quarter, it becomes positive 1 over 2, x to power minus 3. So if you don't mind, let us bring it back to make it positive 3. So this will be the derivative of this function. Okay, that was also a good idea to use GeoGebra because it's good to know about that. Okay, I myself have a little bit of difficulty with the derivative of GeoGebra, but to be honest, I really don't care, but you have to care. Okay, so you need to go and learn this good. The way that I do it for GeoGebra, first of all, I think still it's better to go to CAS view. So we go to CAS view, and probably we don't need the other view, so let me take the algebra off. And we also don't need graphics. Let us take this off. So if you want to take the derivative, so let me put one of these functions there. It's exactly the function that I just did. So let me write k of x equals to, I think this is the way that you have to do it in GeoGebra. So I have 5x to the power of 2, and then I have plus 6x, and then minus 1. If I remember correctly, sometimes it complains about putting this multiplication here. So it doesn't hurt. Yes. This is what I want you to learn because you probably need this. And then divided by 4x squared, 4 times x squared. Okay, so this is the function that I have. But before pressing enter, I think it is a good idea if we go there. Do you have questions?
Yeah.
Yes?
Or the answer shouldn't be 1 over 8x to the 3.
No, because I see this minus 2 will be multiplied by minus a half. So minus 2 goes to the numerator. Yes, so make sure that you don't mess these things up. You know, a over b times c over d is a times c b over d. Yes, so when I write 2 times a over b, 2 means 2 over 1. So 2 only multiplies here, so it becomes 2a, and 1 multiplies here, it becomes b. So it only goes to the numerator. So when you have minus 1 over 4 multiplied by minus 2 means minus 2 over 1. So minus minus is positive, and then it becomes 2 times 1, 4 times 1. And this becomes 1 half. Yes? Was that the question? Okay. Okay, so let us now come back to GeoGebra to see how this will work. So I had the bad experience of pressing enter right away. You can go and learn that. But before pressing enter, I see the derivative sign here. So let me just put that. And of course, I know why GeoGebra writes like that, because GeoGebra is following the quotient rule. And the point is that this is How can we simplify then? Because this is not wrong, this is correct, but it is not the simplified version. Do you know how we simplify things here in GeoGebra? No, it is the function itself. Okay, now if I press this one on the other line, it will give me this. But what is the meaning of this? Usually when you keep it here, there should be, so let me use expansion. Ah, okay, good. So I accidentally did the correct thing. So I expanded that one. And I think you can confirm that what GeoGebra, this is what I want you to learn. It is confusing for me sometimes how to use GeoGebra. But because this is a software that you are going to use in the exam, it's good to know about what is going on. So this is the answer. GeoGebra provided the answer in this form because probably it is using the quotient rule. Okay? But it doesn't matter how GeoGebra gets the answer. This answer should match with mine. So let me go back to the board and see that this answer mine. But of course, in the exam, you just stop there. It doesn't matter. Okay. But if you want to continue, how do you continue? You take the common denominator. The common denominator is 2x cubed. And 2x cubed divided by that is x times. You multiply it there, so it becomes minus 3x. 2x cubed divided by that is 1 times, and 1 plus that. So this is the answer that our GeoGebra provides. Is that right? Yes. And this is the answer that I got. But my point is something else. I want you to be good in how to use this application, because it is sometimes confusing for me, especially by copy pasting and things like that. So I am lucky that I don't care about it. Okay, so but you have to care, yes? Okay, so this is one thing. Let us go back to the board and then try to solve some other problems here as well. This one, I intentionally put them in one problem, not because this is hard, because I want you to understand the difference between these two functions. Okay? The first function is called a power function because the base is variable, the exponent is constant. The second function I have constructed with the same two things here, but I've swapped them. This function is not the power function anymore. This function is called exponential function. So be careful. This is a polynomial function or a power function. This is an exponential function. We have two different rules for them, quite different rules. Okay? For the power functions, I use this rule. For the exponential functions, I use that rule. And they are completely different, you see. So you have to realize that this is the case. So how should we solve the problem now? It is easy. So I can immediately start because they are exactly in the right forms. So L prime of x is equal to the derivative of x squared, probably simplest derivative ever, yes? That's 2x, and then 2 to the power of x becomes what? The last row. So what should I write? Here, 2 is playing the role of that constant c. So this becomes 2 to power x, but this is not enough. I have to multiply it by ln of 2. So that's the answer. But I put intentionally them in one place that you can see the difference. Of course, number 6 is also correct. It's the same story, yes? What should I do that? I didn't wrote the other version of it, but if you want, I can add here. Of course, you don't need it. I want you to see what happens here if I have c and then I have some k and then I have x. In that case, k also goes down, and then you will have c to power kx ln of c. So here I don't want actually use this. I want to just use this one. So how can I use that one? How can I use that one? Because I have a power of, because I have a coefficient here. But this can be solved easily. Instead of 3 to power 2 times x, I can write 3 to power 2 and then to power x. And then here, of course, this is easy. 2 times x to power 3 becomes 2 to power 3, which is 8, and x to power 3. But 3 to power 2 has a better name, and that is 9 to power x. And then I have plus 8x to power 3. So now everything is ready, so I can start differentiation. So the derivative of s becomes the derivative of 9 to power x, which is still, I can use the last row. I don't need this extra formula. So this becomes 9 to power x, but I have to multiply it by ln of 9. And then plus 3 goes down, 24 x to power 2. Okay, let me just tell you that if I have used this formula, this will also be correct. So let me start from here, just only do this first part. So 3 to x. I want to give the role of c to 3, and I want to give the role of k to 2. And then I just copy and paste that formula with those numbers. So the derivative of this becomes equal to k, which is 2, times 3 to power 2x, but multiplied by ln of 3. But these two are the same. Do you agree? Because 3 to power 2x is exactly as 9 to power x. 2 times ln of 3 is also equal to ln of 9. Do you remember? Because in logarithms, you can take this one and put them on top. So you see that you really don't need that extra formula. You could solve it using just the previous formula, but even if you did, the answers are the same, even though it is a little bit different. So if you don't mind, let us see how GeoGebra actually answers that to improve our experiment, actually improve our skills here with GeoGebra. So let me call this function s of x. Is it s of x? Yes. S of x is equal to 3 to the power of 2x. Okay, I'm not sure, should I put this product here, but sometimes it complains. Okay, 3 to the power of 2x, and then I have plus 2 multiplied by x, and then to the power of 3. Yes, that is the function, but let me just press the derivative button so I get this one. Is that right? So then do you remember how did I simplify that? Okay, I just press this one. No, expand, yes?
Yes.
But expand doesn't, of course, work here. Anyway, but this is not wrong. At least this is good. In the previous lesson in Math 3C, whatever I did, it answered wrong. So I don't know what happened then. Okay, but this is correct at least. So 24x squared, and that is this version of this. So that's correct. Good. Okay, so let us continue. I want to wait for you because now this is a little bit lengthy, I agree, but I want to give you time to practice this one. The idea here is the same as idea there. Okay, but I want to wait for you to be able to do it. This is something that you have to learn to improve your skills. Because by the way, most of this chapter is only dedicated to differential rules. I think all of them. Because after that, we learn about the chain rule, which is extremely important, and then the quotient rule, the product rule. Then we start increasing this table to sine function, cosine function, logarithmic functions, and then tangent functions. So, I mean, the whole chapter is about differentiation. Okay? Yeah. So it is extremely important to be good in differentiation. I will wait for you. And in the meanwhile, I can type that function into GeoGebra so that we don't spend so much time on it. Okay, is it finished? No? Okay. Okay, so let me solve it because I want to finalize this lesson today. So this was the function we are supposed to differentiate. You know that you haven't studied the quotient rule yet. So what we are supposed to do, we try to simplify this a little bit. So here, this is, let me write everything, x times. This one can be written as x to the power of 1/2. And then I copy and paste the rest of it. And then divided by, this one is 5, x to power 2/3, yes? Okay, and then I combine these two because I am multiplying with the same basis, so I add this exponent to this exponent, which is not written, so it is 1. 1 plus 1/2 is 3/2. Okay, but let me just do it now. I take this one and divide it by this, minus, I take the other one and then divide it by that, and then 1 divided by this expression. Okay, so then I have to simplify. Simplification needs this rule, yes? If I have a to power m divided by a to power n, I can write a to power m minus n, and I know that if I have a to power n, I bring it up, it becomes minus n. Okay, so what I do here, first of all, these are numbers, so I then divide them, it becomes 3/5. X and x are the same, so I write the same x. I subtract these exponents, so I have 3/2 minus 2/3. So the common denominator is 6. To this 3 times, it is 9. To this 2 times, it is 4. So it is 5/6. So this becomes 5/6. And this is minus 2/5. I do the same thing, but let me just do it in my head. So 2 minus 2/3, so it becomes 4/3. But what can I write for this one? 1/5 is the coefficient. This can be separated and brought this, I can bring it up. So this becomes x to the power of minus 2/3. Now everything is ready to start differentiation. So t prime of x is equal to, so let us just do it this in our head. 5/6 comes here. That 5 and that 5 will be cancelled. 3 and 6 will be simplified, so it becomes 1/2. And x to the power of 1 unit less. 5/6 minus 1 is minus 1/6. Again, this 4/3 goes down. Nothing can be simplified, so 2 will be multiplied by 4. 5 will be multiplied by 3. So this becomes minus 8/15. X to the power of 1 unit less, which is 1/3, yes? And then this minus 2/3 goes down. Nothing can be simplified, so I just simply multiply 1 by 2, 5 by 3. One of them is negative, one of them is positive, so the product becomes negative. And x to the power of 1 unit less, which is minus 5/3. Of course, I don't think GeoGebra will give you this answer. Probably GeoGebra will give you the simplified version. So let us go back here. So I erased everything here. So let us go back and type this function. But by the way, you know that in GeoGebra, you have to anticipate that you need a pair of brackets around them. Yes? Because if you start typing this up to here, then you press the, I don't know, slash button, only one will be divided by that. So you have to anticipate that you need a pair of brackets. So when you want to type, you start with a, so let me write, by the way, let me use another idea. Let me also test this idea. So we go here to f of x, and then I see this symbol. I will talk about this symbol later. This is the Leibniz notation. So let me just press, this means derivative, d dx. So I press this one and it automatically types here derivative. Then probably I can just type my function in. Okay, so let me just type my function in. So let me just use this, only this virtual keyboard. So I will say 3 times I have x times the second root is also here of x. Yes. And then I have to press this arrow button to go out. And then I have minus 2 and then times x to power 2. Yes. And then plus 1, plus 1. Oops. Sorry, plus 1. And then I go outside and then divide. Then automatically it takes that pair of brackets out. And then I have 5 here. But for this symbol, we also have it in GeoGebra. It's good to know it. So you just press this and then you go to functions and you see have this button here, yes. So you press that one. The number on top is 3. And then I go down. This is x to power 2. X to power 2. Okay, but I don't know if we can probably work with it. Let us see how it works. Yes, this is the derivative. And I know that this is complicated, but GeoGebra is again using the quotient rule. So that's why I'm saying quotient rule is not that efficient, but that is not wrong. But this is something that I want to know how to simplify this. I don't see any instructions for simplifications. Do you see that? No. Okay, but let me just use again or this expand, see how it works. Yes, it is much better. So whenever you don't know what to do, just press expand, it works, okay? So this is, of course, it is better than what I have written here on the board. I want you to be able to change my function to this one later, okay? But at least this also works. It seems reasonable. I didn't calculate it that, but it seems correct. Yes, because the denominator, I have a 30, it makes sense, 2, 15, 15. If you take the common denominator, it becomes 30. And then I have 5 over 3, which is the highest one. Yes, that's good. Okay, so now this is one thing, yes.
But that was the complete right answer on the bottom of the board, right?
Yeah, that's correct.
Yes, there's no explanation.
No. Okay, so here, now I want to teach you about higher derivatives. We had this before, yes? So what is the meaning of a higher derivative? It means that you take the derivative, you get a new function, now act this as a new function, take another derivative from that. That is called the second derivative. So if you remember, so if I give you, for example, let me just give you a simple example. F of x is 2x to the power of 5. If I ask you take the derivative of this function or differentiate it, immediately you get 10x to the power of 4. Now give the role of your function to f prime of x and do the process of differentiation once more. What you get is called the second derivative. Okay, and then there is a symbol for that. So you just show it with, in English you call it double prime. So f double prime of x means after finding the first derivative, do another derivative for this one, and that would be 40x to power what? 3. And then higher order derivatives also exist, so you can just take triple prime of x. What the answer is 120x squared. And then these are conventions, but if you want to go higher, you cannot continue adding these dashes. So this is the convention. Up to 3, you use this. But then after that, you put a 4 here, but then it will be confused with the power or exponent. This is why they put a pair of brackets around that. So this means this is fourth derivative, not f to the power of 4. So then what happens if I ask you what the answer is? This is 240x. And if I want to go higher, so I would say f fifth order derivative, which is 240. But what will happen if n is greater than or equal to 6? Then everything becomes 0. So if n is greater than or equal to 6, of course, natural number, yes? But this is exception. There is no guarantee. for this to happen. But if you have a polynomial function, yes. If you continue this process, finally everything vanishes. So my main point is here is not just the calculation. I want you to understand the notion of this one. But still, we don't know the meaning of the second derivative from geometrical point of view. If I ask you what is the meaning of the derivative, first derivative, it is the slope of the tangent line. We can talk about that later. But about the second derivative, still we have some interpretation. For the third derivative, fourth derivative, we don't have that simple explanations. But we need them. Okay? And let me also tell you something. In this notation, sometimes you might see a little bit strange notation like this. What do you think it means? It means the zeroth order derivative.
Isn't that just not the derivative?
It means the same function without doing any derivative. So in this symbol, if you see something like this, remember it means the function itself. Okay? Notation. Okay, so that is also the idea of higher derivatives. Let us go back to GeoGebra. In GeoGebra, you don't need to, so you should be able to give how many times you want to differentiate, but let us see how. For example, I go here. Let me just, by the way, type derivative. Let us see what happens. Yes, so you see a derivative comes in, I press on it, and of course there are some expression variable, expression variable number. I suspect this one is the correct one. Anyway, let us test that. So I type a function, for example, 2x to the power of 5, just the same function I did right now, times x to the power of 5. And then, of course, what is my variable here? I will also talk about why they are asking about the variable. And then, how many times you want to take the derivative. So, for example, let us take 4 derivative. So, I put 4 there. It means the derivative of the function 2x5, variable is x, how many times? 4 times. And that is 240x. So, you really don't need to just do it every time. So you just give the number and it will give you the exact order derivative there. Okay, so do you think that I have a copy paste version of this? I always like to play games. Yes. Yeah. So here, let us just take the derivative here. I mean, it's a little bit complicated probably here, and then let me paste this one. Okay, let us make GeoGebra suffer a little bit. So, and then we take the variable, let us take 10 times. Let us see how it goes, yes. No, it's not that bad, okay? But this I don't know, can I trust it? But I think we can.
Can you do it 20 times?
Let us do that, yeah, you want to suffer even more, yes? This is the bad thing in human nature, yes? Yes.
Holy shit.
Yeah, but the functional form is not probably changing. No, because you know about mathematical induction. So, for example, I can give you a function and then you can try to see that if you can find a pattern for the derivative. So, not always this is the case. But, for example, this function is possible. What do you think? Let us take this function, do some exercise together. So, here. For example, what do you think? By the way, if I ask you to differentiate it over and over again, how do you do that? So the first one, we have it in our memory. So let me just write f of x. So the first derivative is, so let me write it like this. This becomes x to power minus 1. So when I take the derivative, minus 1 goes down. And then I have x to power what? Minus 2. And then let me take another derivative. What will happen, do you think? This minus 2 goes down, so it becomes, because whenever you want to keep the pattern, if you want to have the pattern, it is better not to calculate things, because you want to see the pattern. Minus 2 goes down, minus 1 times minus 2 is just 1 times 2 because minus signs cancel. And then what do I have? I have x to power minus 3. Let us just do one more. Probably we'll be able to guess something in general. So what do you think will happen now? Minus 3 goes down, but this time it becomes negative. So it becomes minus 1 times 2 times 3, but x to power minus 4. Okay, hopefully it should be clear for you what will happen if I continue this process. By the way, this is not always possible to find a nice pattern. This is why I didn't expect that probably this can do it so easily. It might be there are some patterns. And of course, now I realize, yes, I was stupid, because this can be written of this form, and then using that I can find the pattern again for each one of them. Yes, but let us just do this simple case. Can you guess what will happen for the last one, nth one? Something is easy to guess. This x part is easy. Yes, because definitely you agree with me there is an x involved, but the power is the exponent will be important. If I have one derivative, the exponent is negative 2. Yeah, so what is the exponent here?
It's minus n plus 1.
So is that right? Do you mean this or not?
No, minus bracket.
Yes, this is correct. Everyone agrees? This seems to be the power. Okay, but what do you think will be the coefficient here?
Is it 1 times 2 times 3?
Times up to n. Yes, 1 times, 2 times, 3 times n.
Yes.
But one of them is negative, the other one is positive, one of them is negative, the other one is positive. We had something like this game in Math 5, do you remember? Positive, negative, positive, negative. How do you keep track of that?
Plus minus.
Work on your damn memory, okay? Yes? So that I told you there, so you just asked me today. Yes.
When the power is even, it becomes positive.
So now what is the point? The point is to play with this, yes? It's a combination of this. Might be this will work, might be you need to add minus sign here to adjust. Because if it is 1, it is negative. And when it is 2, it's positive. 3, negative. So you see, whenever it is odd, you have to have negative. Whenever it is even, you have to have positive. Yes? So what do you think what will be at the end? I should write minus 1 to which power? Okay, let us check. Yes, n is correct. Because if n is odd, then this minus 1 to power odd becomes negative, and that this matches my expectation. That's correct. So that's the formula we were able to guess. By the way, there is a name for this. You will learn it in Math 5. This is called n exclamation mark. And that's called n factorial. Okay, so we will learn about this in Math 5. But here, f of n of x, I can write it as minus 1 to the power of n times n factorial. And then let us bring this back to make the exponent positive. So what will happen? This becomes x to power n plus 1. But this is one of those exceptions that we can come up with a formula that gives me any power, any derivative of that one. But the problem is not finished mathematically speaking, because just that was a guess. When it is finished? When I can prove it. What do you suggest to prove it? You need to know.
Mathematical induction.
Induction. So why is that? Because it is something about a natural number again. So this is mathematical induction. So it doesn't matter. I told you that mathematical induction is extremely powerful. And I really recommend you to prove it using mathematical induction. Okay? Yeah, I probably can do it in Math 5, but remember that. Okay, we come back to this in Math 5. Okay, so that's what I'm saying, that you shouldn't expect that you should be able to get such a nice formula for any function that I give you. Sometimes it is not possible at all. Okay, so this is the case. Okay, so for example, if you want, we can come back here, continue our game. So let me see, now I can have a better guess to make this suffer, yes? So we go here, and then probably we just change a little bit. So let me see if I can do some changes. So I have let me just use quotients for the time being. So x to power 2, and then plus 1, and then I go and write 2x to power 3. No, 2 doesn't matter that much, plus 3x. I always forget to put these dots. I don't know if they are eventually important or not. So this is also x, and let me now put a 10 here to see how it with this one will work. No, let me also add 1 to it. Yes, that's good. Plus 1. Oh, now it becomes complicated, yes? Yes.
It doesn't even look that complicated.
Yeah, it is, isn't it? So I mean that this number, so let me just do it 1 times.
Yeah.
Okay, and then you see it was not that complicated. So for 1 times it is this one, but you cannot do this. This is one of those cases, even if you want to do it 1 time, you have to wait until the quotient rule, because we don't know about that. But then, for example, if I increase it to 2 times, I don't know, you see, hopefully, I don't know if we can find a pattern what is going on. I even don't think we can find the pattern. So let us make it 3. Yeah, it works. By the way, let us make it, who cares? Let us make it 300.
Yes.
No, it doesn't know what to do. So it's calculating. So it becomes extremely hard. But then, do you know how should we stop GeoGebra? No, question mark, yes. But let us make it up to 30. But I think all from alpha can calculate that. I think up to 30 it should be able to calculate.
I think that's a big
Oh.
So that would be your derivative. So remember, I will give you this that you have to calculate by hand in the exam. So prepare yourself. Okay, so good. Anyway, so now you learned some things in GeoGebra. We also learned about the derivative. Now, do you see why GeoGebra is asking about a variable? This is I want to talk about here. There are some symbols in your book. All of them you need to know. Mainly I use this symbol, but I want you to know other ones as well. They are very common when it comes to derivatives. So assume that you have this function y is equal to f of x. Sometimes people write y prime. Sometimes people write f prime of x. Sometimes people put a capital D for derivative, and then they put f of x in front. And sometimes they write a little bit strange way, which is the Leibniz notation. dy dx. So this is the Leibniz notation. Okay? And you read it dy dx. By the way, it is not very strange that you come up with this, because do you remember what was the definition of the derivative? The definition of the derivative is f of x plus h minus f of x over h. Okay? So h goes to 0. So if I want to draw a picture for you, if this is your function, let us say this is x, let us say this is x plus h. This change that you see here is a change in x. So you can call this is h. This length is h units. If I ask you what is this length, you would say this is a change in x. So another way to say h is to say delta x, how much x changes. Okay, so then you take this away and write delta x. In the numerator, what is happening? F of x means this length. F of x plus h means this length. I am subtracting these two lengths, so I am getting this. This is a change that happens in y direction. So that is delta y. Yes, so another name for h is delta x, the change in x variable. Another name for f of x plus h minus x is the change in y variable. So it is good to denote it by this. And then you have this limit h goes to 0. And Leibniz took this one probably and wrote dy dx for very small change in y and very small change in x. But this is a little bit confusing. Do not consider them separate. Consider this as one entity. Do not see it as a fraction. Even though originally this is a fraction, but do not look at into this as a fraction. The whole thing is, it means this. But why this is sometimes good? Because I can give you a function with a squared x cubed. I am using another letter here. Of course, by convention, most of the time we know x is variable. But sometimes this is not the case. People can ask you, calculate this. Okay, can you answer me, what is this one? dy dx. It means that take the derivative of y, but this is emphasizing that x is your variable. Yes? So what happens? What is the answer to this? A plays the role of a constant.
Yes.
And a to power 2 is also a constant. So I don't care about the constant, I just take the derivative of that one. And then if you want, you can write it in simplified form, 3a squared x squared. But for some reason, might be, you are interested to make a variable. So then they use this notation, dy dA. So what does this mean? It means that go back to the same function, but for some reason, take a to be your variable. Okay? And x will play the role of the constant. Okay, now can you tell me what the answer to this is?
It is x to the power of 3.
X to the power of 3 plays the role of your constant now.
Yes.
You just, this is 2a exactly. And the answer is 2a x cubed. And they are different.
Yes.
So that is why sometimes when you have more than one variable and you want to be explicit about the name of the variable, this is a good symbol. And that is why GeoGebra is asking you. So let us go back to GeoGebra. I pressed again, I want to give you the same function I was talking about. So derivative, I take the derivative, but here I take the derivative. How many times we want to differentiate? Just one time, so I don't need to choose the number here. I go here, variable. I put the expression. It is a to the power of 2 multiplied by, I think it's essential this one, put the multiplication, x to power 3. Okay, the first one I choose x and then find the answer. So the answer is 3a squared x squared, which is the font that I got here. But I will copy and paste, hopefully. This copy and pasting, I really don't know what to do. The standard Windows keyboards, do you know how to do that? Okay, let me highlight it. Yes, Control C, hopefully it will work. And then I come here.
So what you can do is
Okay, it worked. Okay, forget about it. And then I put a this time. Yes, I am just giving GeoGebra that no, a is my variable. For some reason, x should be held constant. And that's the answer to ax to the power of 3. So that is the good point about Leibniz notation if you need to emphasize. But of course, I will not emphasize. Whenever I give you this in the exam and ask you to differentiate, I always mean x. If I want to say something else, I have to be explicit, sorry. But there is a little bit weird notation I want to go. If I want to go higher derivative, you don't have any problems here. For example, for the second derivative, what do you write? This becomes y double prime.
Yes.
The second one becomes what? F double prime.
Yes.
But this is also important to realize. This just becomes d to power 2 without any pair of brackets around. Okay, and then f of x. And the most weird thing is the other one, which is dy dx, but you put 2 here and 2 here.
What?
Okay?
That is really strange.
No, it's not very strange. So let us go one more higher. What happens in these symbols? Y triple prime, F triple prime. What should I write here? d to the power of 3, because this is really power. If you look at the derivative as an operator, this operator is acting 3 consecutive times. So that's exactly the meaning of an operator to a power. But forget about it. And then what should I write here? dy dx, 3 here, 3 there. Yes?
Why is it not on the y and x?
No,
Is it just decided or is it?
no, I think might be that is natural if I want to understand that.
Okay.
Yeah, might be we can talk a little bit about that later. Yeah, I think I tried to understand it once. It is natural to put 3 here and there. Yes. But anyway, you need to learn it until I think what was my reason before. Yes. Anyway, so I want you to get familiar with these notations as well. Let us see what else we have. For example, if I ask you to calculate the derivative at a number, how do you do that? I'm just reminding you about these things. For example, the function is 3x squared. If I ask you to calculate f prime of 1, and if I calculate, let me make it 4, and let me calculate f double prime of the square root of 2. So you want to calculate the derivatives at some particular numbers. So what we're supposed to do? I take the derivative first and then put the number in. So for this one, you have to calculate what? The derivative, which is how much? 12x to the power of 3, and then replace x with the number given, which becomes 12. And then you need to take the second derivative of x if you want to calculate this. 3 goes down, 36x squared, and then you put f prime, and then you put the square root of 2 there. So this becomes square root of 2 to power 2 times 36 is 72. So you have to first find the derivative and then replace the number. By the way, that's also good to see how GeoGebra answered that one, because that's also good to know. This I really don't know how to put in GeoGebra. But let me just calculate. So let me just type that function f of x. This is good, by the way. You learn about this yourself, and if you learn something good, you can also come and present it here. Okay, so exactly like the book club that you started now. Yes.
Of course, we have
Have you forgotten that completely? Okay, so you are very, very fast. So here we type that one, and then let me just type, I don't know if it works, f prime of 1. No, it returns back, but this is extremely strange, because what if I type f prime of x? Now it suddenly stopped working. Do you remember it was working in this way when I started? It is very strange. Might be I don't understand how to work with it. Because I know what to do. I can write derivative. I realize now, so I can write the derivative expression variable. Okay, so expression is 3x squared. You really have to know these things very well, because in the exam you really don't know what is happening to you. Okay, so this is x. Okay, and then when I differentiate it, I get this one. Then you can go here and substitute. But that's a little bit a strange way, isn't it?
Yes.
So I substitute with 1, and then, okay. Still I have to say, okay, what is this one? 6. Yes, so this is one way, but I don't think it's an efficient way to do it. For example, if I just go here and type derivative, and then I go here because I want to have the second derivative. So what is my function? It is 3 times x to the power of 2, and my variable is x. No, it was x to power 4, sorry, here. So let me make it 4. And then my variable is x. I want to have 2 times derivative, so the answer becomes this. And then I probably have to choose this. I don't know what's happening. I go here, And then, no, it's very strange. So I only change this with the square root of 2. Let us see how it goes. It doesn't type here. So why it doesn't type there? Okay, anyway, 2 to power 1/2. Anyway, so that's the answer, and then put equality. Okay, finally 72. But anyway, so you need to find a very wiser or efficient way to do these calculations. Okay, any questions? Okay, have a nice weekend. Thank you. Okay, by the way, next time we start the real lesson of Math 4. Okay, so this was just repetition from Math 3C. Yes.